I would like to mention that homework is there for you to do it. Good, right? There's homework now, posted at 10:50. It is due 10:50 next week, Wednesday. Okay. Homework is easy enough. It is about single phase flow. If you don't know anything about two-phase flow, you can still do it. Okay. We will review it so that we make sure that you can actually doing it for sure. All right. Mohammed Ramadan, still not here? Okay. One of the university excuse to miss the class is that you haven't enrolled yet. The university allows you to enroll late. Okay? But if you enroll already, but you don't come to class, that doesn't count as a university excuse. Okay? You should have done that. Correct. Okay, when I go to the blackboard, what you see is, anyone use blackboard? First time ever? Of course, okay. Go to course homepage, placeholder. You see homework. Okay? And this homework, it takes some time to do it. Alright? The amount of time that I expect you to spend on homework for each week for 3 credit hours course is, okay, let me ask one of you. George, how much do you think you should expect the amount of workload? How many hours? To do the homework, review the class material, how many hours? 4? Twice as the number of credit hours. So this means number of credit hours is 3. Twice of the number of credit hours is 6. So you would expect about 6 hours of time to spend outside the class to do the homework and to prepare for the class. But it's not that difficult. Let me show you how does it look like. Question number 1. Write 2 to 250 words in English, okay? Everyone sign it? So this is just about 200 to 250 words. And you want to tell the usefulness of multiphase flow in pipe subject for petroleum engineering discipline. Why should it matter to you? And you should tell several things. Use scopus.com. This can access when you use university network or VPN. Or if you want to do in the library. In the library, there's free computer for you to use. Also, we have a drop-in computer lab. Have anyone used drop-in computer lab before?
I think nobody uses it.
Nobody uses it, but you actually allow. Okay. Drop-in computer lab, TTU. For engineering department, we have computer labs and our civil engineer, mechanical engineer. That's computer lab. This one is the old petroleum building. Okay, this is the time that you can go there and sit. You may need to do that because I asked you to use scopus.com to search for the literature. Read a couple lines, the introduction part of the literature, to write the above essay. So you want to tell why should this topic matter at all? What is the importance of this topic? So I know that you understand it from what you learned from me. In addition to that, you will cite a literature. You may say, okay, this paper from this group of researchers say that multiphase flow is used in nuclear reactor and also in pressure drop subsea pipeline calculation. So you cite just 2 papers. So 200 words, it's not quite a lot. Okay, 200 words is how much? From first line to here, this is 164 words already. Okay, 200 words is this is 300 words. So it's not a lot, 200 to 250. Second question, calculate friction factor. I just told you how to do it, so you should be able to do it. Number 3, temperature profile, pressure profile with some assumption. We are going to talk about it now. Okay. And number 4, calculate the thickness of paraffin deposition that make the pressure drop increase 20%. This may seem to be new, but don't worry about it too much. Paraffin deposition is something that deposits in the pipeline and it makes the flow area to shrink. Okay, so if you have 1 millimeter of paraffin around the pipe, then the flow area reduces. When the flow area reduces, the fluid may flow a little bit faster and we have more pressure drop. So if the flow area reduced to be very small, we have a lot of pressure drop. So the question is just how thick should be that deposit to make the pressure drop go up by 20%, like go up from 100 to 120. Okay, and this is a horizontal flow. The equation is 2F rho V squared over D. Okay, that is equal to minus dP dz. Account just for frictional pressure loss. No gravitational term is needed because this is a horizontal flow. Okay. This one you should be able to do it already. This number 3 we cover in this class. The objective of this class is to review more material for single phase flow. Okay, we're still in single phase flow. So this part you get it right, how severe slugging happen in the field condition. The equation that you use for question number 4 is just this one. Minus dP dz equal to 2F rho V squared over D. And it is smooth pipe. I assume that the deposit is smooth and the pipe roughness is 0. So you use this equation with Glassier's type equation. Glassier's type equation is this one. See this? If you use Fanning friction factor from Colebrook equation, you can also do it, but it is somewhat more difficult, kind of a lot more actually. Use this one, make everything easy. What I would suggest you is to use pressure drop ratio. Okay, pressure drop ratio means this term before and after wax deposition. Okay. For those of you who have done similar question already, do it again without looking at the solution that you might have from any other class. Okay, it's not that difficult. All right. I show you how to use successive method to calculate Fanning friction factor. So this is one equation, one unknown. We can use Newton-Raphson to do calculation too. Okay. You did it by your successive method. That's pretty easy to put in calculator. Okay. For one equation, one unknown, we can use Newton-Raphson. This course is not to teach you how to do numerical method, but just tell you a little bit so that you know that it can be done even in Excel. Okay. Newton-Raphson means the next guess of friction factor equal to the initial guess minus some function divided by slope of that function. Alright? So we have one equation, one unknown, which is this one. Right? 1 over square root f plus 4 log base 10 of this. You see this? If we put the right value of friction factor, right value of f, we put it in. What happened, Tolani? Correct. If we put f, the right value of f, this term, the first term will be equal to the second term, and it will be 0. If the value of f is not correct, it will not be 0. So we are trying to find value of f that make this whole thing equal to 0. Okay? If I don't use any numerical method, I do it in Excel. I just plot this function at various values of f and find out which f that make this function equal to 0. You still with me? Tommy Tope?
Yes.
Alright. You know how to do that in Excel, right?
So you plot?
You plot. You do the plot. So first column will be friction factor. So you say friction factor equal to 0.01, and next one will be 0.009, 0.008, 0.007, 0.006, and so on. And next to that column, you calculate this. What you will end up is some kind of graph. If you put the right value of friction factor, this whole thing will equal to 0. If it is too small or too much, it will not be 0, correct? And you can plot graph in Excel and find out which point that make it equal to 0. Instead of doing that, we can use Newton method. Newton method means you start with the initial guess, that point. From the initial guess, we calculate this value, which is script f value. Okay, so we put initial guess of f, put it in there, calculate this right hand side, and then we get that f, which is this value, right? And next step, we calculate slope. We calculate slope, which is f prime. After we calculate slope, then we want to follow the slope to go to this point. To make it clearer, put it this way, maybe it's not that clear, right? You need Excel, right, to show you. By the way, the project, you need some kind of calculation, but you don't even need to do anything in VBA. You can if you want, but you don't need to. You can do everything in Excel front. Okay, and you can also use GoSeek. GoSeek is allowed. Okay, you can use GoSeek. Alternative to that is use Newton method. Okay, this is to show you how to solve it different way. So we have function f, capital F, and small f. So small f, we say, okay, 0.0001. Don't see it, right? Okay, enlarge it. Equal to this one multiplied by 2. Okay. And this function f is equal to 1 over square root f sqrt of this term plus we need Reynolds number and friction factor. Reynolds number epsilon d. Okay, epsilon equal to 0.0002. D is 0.05. Reynolds number 30,000. Okay, that f 1 over square root f plus 4 multiplied by log of epsilon f4 over d f4 again divided by 3.7 plus 1.256 divided by Reynolds number divided by square root sqrt of that term. Done. So I get 300 something, which is too much, right? LOG in here will be log base 10 already. So I plot my graph, insert graph, and when I look at this graph, somewhere close to 0, maximum, let's say maximum of 50, minimum. So you see, at some point, it crossed 0. The value of f that make this thing cross 0, that is the right answer. Okay? So instead of trying to plot graph, replot graph, plot it again, instead of doing that, to search, so basically we try to search for the value of somewhere between 0.005 and 0.1, right? Somewhere between this. Instead of doing that, we can use Newton method. Okay, Newton method, everything can be done in Excel without using VBA. So we start with initial guess, 00001. That is initial guess. Okay, and we have to calculate function value and slope, right? And then we can calculate the next value. So function value, I go back. Function value is this whole thing. That is that function value. So actually this is the function value. See, this is the function value. Okay, we already have f, so next step we want to calculate. F is, okay, let me copy. This whole part is function value. Next, I want to calculate f prime. Okay, f prime, how do we do any of that? So instead of take the derivative, let's use finite difference approximation. Finite difference approximation means we use the same formula, okay, but this time we add a little bit of small numbers, plus 1e minus 6, okay, and over here, plus 1e minus 6. So we add a little bit into it, and then minus that whole thing, oops, and everything divided by 1e minus 6. Okay, let me put parentheses across this. And everything divided by 1e minus 6. What is that telling you? That is a slope, right? Slope of some function equal to f prime. F prime can be approximate. Let me type it instead. That may be better. So we have f prime can be approximate from f of x plus small number epsilon minus f of x divided by epsilon. Good, right? Now it's visible. So basically we use that formula to do the approximation. That is the definition of the slope, right? The slope is the derivative, basically. That function add a little bit minus the current point divided by epsilon. So now we have F prime. It looks like that. And you will notice that it's kind of messy if you do it in here. If you do it in VBA, it's a lot cleaner, right? But my point is, you can do everything in Excel front. Okay? And next step is the previous value. Let's check the formula. Previous value minus function value divided by slope. So previous value minus function value divided by slope. Okay. And we redo the same process. So what I do is just do the drop down like this. Oh. Is it done right? Not really.
Just step by step, each.
So this one is, let's, so what's wrong with that? Maybe some 308 is fine. This one probably not fine. I delete this part and add something more. Whoops. Add epsilon plus 1 e minus 6. This is f plus epsilon. And then I redo this whole thing again. Maybe the problem is over here. I hope. So now I use e plus epsilon in doing the calculation. And the slope is equal to this minus that divided by epsilon. We didn't do anything wrong. So that is the f and f prime value. Oh, I think the next value that I use should not come from here. I think I got it. What's wrong with that? So what I did is the function value. This time I have to use this cell to do the calculation. Okay, not this part, because this part is for some other calculation, right? I used the wrong one. And probably same thing over here too. And now it converges. Look at that. Nice, right? You can actually do it faster, but use seek. Okay. Why do we do all this? Because sometimes you want to check similar thing in another way to see if method one that you did is correct or not. And okay, so you have several methods to check each other. Alright? So now you know how to do, I will save this and upload on the Blackboard. Okay. So now you know how to do Newton method. Just use Excel front without VBA. Any other numerical method can also be done by just Excel front. Okay? It doesn't need VBA. But if you do it in VBA, the formula will be a lot shorter than that. Okay? The formula will be a lot shorter than that. So now I know for sure that you can do this because I go over the example. So basically, you can do this, right? Put the value in, do finding friction factor. I know that when I upload that on the Blackboard, it's kind of the solution for the homework. But please try by yourself to see if you can do it or not. Okay. This part actually we go over it already. You remember this successive method, okay, in the calculator. Alright, so next step I will tell you how to do heat transfer calculation. For heat transfer calculation, we start with the governing equation. Okay, this is the governing equation. Okay, thermodynamic law. We have the form of total energy equation. So total energy is kinetic plus gravitational term plus enthalpy. Okay, this is total energy of the system. And Q is the heat added to the system. W is the work done on the system. So this kind of makes sense, right? If we add heat, do some work on the system, the energy of the system should go up, right? So if we do some work, like I lift this cell phone up, so I do some work, the energy of the system go up, potential energy go up, right? So this is a governing equation, and this is in the D form. Enthalpy is defined like this: CP/dT plus the change in the volume multiplied by dP. Okay, next slide is from Burst Stuart Lightfoot. Oh, not yet. It's that one. So the total equation after we substitute everything here will look like this. So Q, heat added to the system or heat removed from the system, will be this part. If we add heat to the system, we have T infinity, which is environment temperature, minus T. So for ideal gas, or sometimes that you don't consider the change in the V hat. V hat is not velocity. Small v is velocity. V hat is volume per unit mass, specific volume, 1 over rho, meters cubed per kilogram. That is V hat. See this equation? All units spelled out over here. Alright? So let's go over some example. This example, it is nice if you can do it. If you cannot do it, it is okay. Will it be in the exam? No. I can say no, okay. But we want to go over it. The reason is, I want to show you that the heat part that is dominating the system is not gravitational, it's not kinetic, it's really the heat that transfer. So this system is flow in the heat exchanger. Okay, 200 pounds per ounce of dry air enter inner tube of the heat exchanger, showing in this figure at 300 F and 30 psi air. Okay, the velocity of inlet velocity is 100. Okay, the air leaves the exchanger at 0 and 15 psi air. So temperature go down and pressure go down. So who's next? Yao Chen. When we have gas go through the heat exchanger and we have pressure drop, why should temperature go down? What is the reason that temperature go down for this particular case when we flow inside the heat exchanger? Because it is a heat exchanger, right? Because it is a heat exchanger. So basically we have cold water, coolant flow in the jacket. Coolant flow in the jacket. So cold liquid come in and hot liquid go out to take heat from the dry air. So this is the heat exchanger. The reason that the temperature drop is because of it is a heat exchanger. So you can have temperature drop without using heat exchanger. For example, flow through a shock. There could be a lot of temperature drop. Next, Vanguard alcohol. Why is that?
What do you call it again?
What is the name of the phenomena that telling us that we have temperature drop because of pressure drop
Well, we have that.
for the case of gas.
Because that's all the law of PV equals.
Yeah, it's follow the law, yeah. What is the name?
Okay.
Name. Isa. JT, what's JT? Are you familiar with JT effect? Joule-Thomson, okay. At low pressure, the drop in pressure will make the temperature drop. That's why when we see gas flow inside the tube, we can see ice outside the tube. That's Joule-Thomson effect. If we have high pressure, the drop in pressure can make temperature go up. High pressure means 10,000 psi or 5,000 psi. But if you have 50 psi, like in the Thai, the pressure drop can cause the temperature drop already. That's Joule-Thomson effect. Okay. This one is not really Joule-Thomson or anything. It's about heat exchanger, so it's different. So the air leaves the exchanger at 0 and 15 at 10 feet above the exchanger entrance. Calculate the rate of energy removal across the tube wall. Assume turbulent flow and ideal gas behavior. And use the following expression for heat capacity of air. Alright, who's next? June or Une? How do you say it? In Norwegian? Juna.
Yeah.
What about Husoi? In Norwegian will be what? Husei. Una Husei, okay. So how do I get this function? If it is not given, where should be the source? Cp equal to something multiplied by T. Where do I get it from? You see this function?
Yeah.
If it is not given, how do we get it from? Okay. It has to be from some book or website. I cannot just pop up, hey, Cp equal to 3.3. No, we cannot tell that. One of the sources is NIST website. NIST website can give Cp formula for pure component. Air is not pure component. Air has mainly nitrogen, 79% nitrogen, and a little bit of oxygen, a little bit of carbon dioxide, argon. So you have to mix them together. Easier way, you open Perry handbook, chemical engineering handbook. You tell that formula for dry air. Question. The main question is, do you have that book? Okay. If not, library have it. Okay. So if you do the research, you may need it. For now, okay, Cp is given like that for dry air. And this is a unit, okay? So what happened next is, there's a bunch of formula. Basically substitute everything into the governing equation. The point that I want you to look at is this. You see this term? 1/2 V2 squared minus V1 squared. This is the energy change due to kinetic energy, kinetic term. Kinetic term, look at this, 0.093 BTU per pound mass. 0.093, that is kinetic term. Okay, the derivation is this. The point is not for you to be able to do it. Okay, kinetic term is 0.093. Gravitational term is 0.01. That is gravitational term. So the change of the system energy due to gravity is 0.01 BTU per pound. I think this have to be M, not F. What about the change due to enthalpy? The change due to enthalpy is minus 72. Okay, we compare minus 72. So at the end, Heat removal, we use 72 minus that, minus that. One of them is kinetic term, one of them is gravitational term. Add them together, we get heat removal. Okay, so what I want you to understand is this. We start with this equation. We calculate the change in the energy due to the change of the velocity, the change due to gravity term, the change in enthalpy equal to heat plus work. Anytime that there is a temperature change, very frequent, if not always, very frequent, this term dominates. Okay? If your fluid or gas change temperature, if the temperature change, gravity term, not that much. Okay? This term, velocity term is not that much. So, this is for gas. For liquid, gravity term may be a little bit more. Yes.
So the gravity term that you talk about, here now we talk about heat. We're not talking about mass, right?
Okay. Yes, yes, yes.
Can you explain the phenomena that make that gravitational element considerable? And how does it affect? This is
Why should we consider gravity term at all? Gravity term come in the energy balance. The change of internal energy equal to heat that added into the system and work added into the system, right? Or plus together. The change of the internal energy is the change in the velocity, the change in gravity term, and change in enthalpy. The case where the gravity term can dominate is really when you do some work on the system, temperature doesn't change, but elevation change, speed doesn't change. So initially it's stop, right now is stop. So work that I put into it is to accelerate this object and then to decelerate and stop it. So that is work that I added into the system. And this time gravity term can dominate. When you lift something that is heavy, that's gravity term. So for flow of fluid that has the direct heat exchange or direct change of temperature, look at that. You see, 72 is a lot more than 0.093 and a lot more than 0.0128. And this is vertical flow. So for the case of gas flow up like this, we can neglect these two terms, right? And it will not make that much of the problem. For the case of liquid, if you want to know if we can neglect it or we cannot neglect it, do similar calculation, okay? Use this thing. This is like a template for you to put something in and get something out. It will be better if you understand, but will it be in the exam? This exam? No. But if you get PhD, you should know it, okay? So, question, yes?
That was just one. What about the unit, BTU?
BTU.
Yeah, what was that?
BTU. You're not from British, right? It's British thermal unit.
Oh, no.
Yeah. British thermal unit. What is the conversion? There's a conversion from BTU to Joule.
you have it in this slide.
Which slide? This slide? Previous one? This one? Okay. 1 BTU is that much pound mass foot square per sec square. What's the unit do you use in Norway? SI.
Yeah.
SI unit. Yeah. For this particular example, it's not SI. There's a conversion for BTU to SI. I don't know right now, but if you Google it, it pop up.
Yeah, but it's like energy over mass, like the
I think it is the amount of energy that heat 1 pound of water to have temperature up by 1 Fahrenheit. Is that correct? 1 Fahrenheit. So that is BTU. It's Joule, it's equivalent to Joule. It's the energy unit, it's not watt. It's not energy per unit time, it's just energy. Okay. Alright. Right now it's 11:40. Let me change. Oh, let's continue for 5 minutes more and change the battery. Single phase liquid heat transfer. For single phase liquid heat transfer, we have to, this is another example. Do the calculation of temperature drop in horizontal subsea pipeline. Subsea temperature is 40 Fahrenheit. Pretty cold, 40 Fahrenheit, but it's above freezing point. We neglect viscous dissipation, neglect the change in density and the velocity in the energy equation. We can do that, right? I showed you it's not that matter. So at the end, when we put everything into the energy balance, the form of energy balance, we have this equation. Okay? dt dz equal to minus u pi d over m dot cp multiplied by this. So basically, the temperature drop along the flow direction equal to heat loss into in the radial direction. Okay. Heat loss in the radial direction causes the temperature drop. Make sense? So if I have fluid flow, inside is hot, outside is cold. Heat transfer this way. Okay. Because of heat come out radially, it makes the temperature drop with length. Okay. And that has to conserve. So when I say radial heat transfer equal to axial heat transfer is some kind of this mCp multiplied by dt. That is axial heat transfer. And this one is radial heat transfer. Okay. This equation comes when we substitute every term into this part. See? Or this one. See this one? dz is over there. So we just, this term is gone, this term is gone, this term is gone. Move Cp at the bottom. Move the dz over there. Then we have this equation. Alright, it's about time. Sorry about that. Won't be long. Forget to charge it. Oh, it's still good. I think it will last for a while. All right. You see this capital U? That capital U is overall heat transfer coefficient. Overall heat transfer coefficient is the combination of 1 over HIRI, this term and that term. 1 over HIRI. HI is convective heat transfer coefficient inside the pipe, or fluid inside the pipe. HO is convective heat transfer coefficient of seawater. This middle term is a conduction term, conduction kind of resistant for heat conduction. So if we have several layers of pipe, we add more term onto this part, okay? So if we have this pipe, so this distance is Ri, and this distance is Ro, we use this formula. If we have another layer, so you have this as Ri and that as Ro. If we have another layer, good. All right. Who's next? Yuan Chan Li. What is the unit of capital U? What do you think? Pardon me?
You said capital U.
Yeah, the unit of this term, capital U.
Joule.
What else? Let's make it a little bit easier. Will this help? Unit of H is watt per meter square per Kelvin. Okay. U is same as H. So unit of U will be same as that. Make sense? Okay. T is the ambient temperature. Ri is capital D over 2 or the inner diameter divided by 2. Pipe thermal conductivity is watt per meter per Kelvin. Okay. And I have the question here. Oil specific gravity Cp is around 2000 Joule per kilogram per Celsius. Okay. What is the oil specific heat capacity in the unit of Joule per kilogram per Kelvin? I put a little note here. T in Kelvin is T in Celsius plus that much. George per the mole. Okay. You have calculator? Alright. So Cp in the unit of Joule per kilogram per Celsius is 2000. If I change the unit to Joule per kilogram per Kelvin, what is that going to be? So what do you do? 2000 divided by something?
No, it's gonna be same.
Do you believe her?
I guess I do.
Oh, you guess you do. Okay, it is the same, alright? So you don't need calculator. So next will be Danny Perez. Why should it be the same? Even though we change the unit from per Celsius to per Kelvin.
What's the thinking about?
Why should it be the same? What is the reason? Yes, it is the same. When we change the unit from Joule per kilogram per Celsius to be Joule per kilogram per Kelvin, Cp value still stay at 2000. Why should it be the same? Sweta Puvada.
Because it is per degree or per Kelvin, so it is just pi 1 and it's the same for both. The change is the same.
The change is the same. Okay, that is the point. So let me ask you this question. The amount of energy that make this object to have temperature go up by 1 Celsius, is that the same as the amount of energy that make this object temperature go up by 1 Kelvin? Same, right? Because the increment 1 Celsius and increment in 1 Kelvin, they are the same. So when we look at the definition of Cp, when we do calculation is, okay, mCp delta T equal to heat. So mCp delta T equal to heat, which is Q. So Q equal to m delta T. This one is Cp, right? So Cp will be, if we do this one, probably m dot. So m dot is kilogram per, is it like that? Joule per Cp. I have Joule per kilogram per Kelvin, so it's just m Cp MCP delta T equal to Q. So Cp is Q over M delta T, right? Q is Joule per kilogram per delta T. The unit of delta T, whether the delta T is delta T in Celsius or delta T in Kelvin, is the same. It's not absolute value. The time that you want to use absolute value is when you do PV equal to nRT. Okay, when you use gas law, that is absolute value. All right. Okay, the above dT/dz equation is valid for very large or very small C pipe value. Next is Siri Salvesen. How do you say your name? Yeah. One more time, please. C.A. Salvesen. Okay. So, valid for very large or very small CP?
Very small.
Very small. Next, anyone want to say otherwise? Your way? What is your answer? Very large or very small?